right, let's get started. Hi, everyone, and welcome to today's Payload webinar. I'm Mo Islam, your host for today. We've got a great conversation lined up with 4 exceptional guests from across the full stack space ecosystem, and we're going to explore one key question, which is what happens when you bring modern computing, real-time AI, and orchestrated data infrastructure into orbit, and why is it changing how space missions are built, deployed, and scaled? If you think about today's satellites, they generate more data than ever before, but traditional architectures can't keep up. You get downlink bottlenecks, you get latency issues, and clunky processing workflows that are holding back everything from ISR to kind of disaster response and a whole other set of use cases that we'll talk about today. The good news is, though, that's starting to change. A new generation of infrastructure, combining space-grade compute, onboard AI, and distributed orchestration is making it possible to process and act on that data in orbit. So we'll break that down today with some of the people building it. So quick introductions. We have Jason Cerundolo, CEO and co-founder of Colossus, Stefan Amberger, co-founder of Tilebox, Gaurav, Bajaj, co-founder of Little Place Labs, and then Aiden O'Leary, CTO and co-founder of Modulate Media. Before we jump into today's conversation, gentlemen, I would love just to go just around the horn, quick kind of introductions from each of you guys. Also, big thanks to our sponsors, Colossus and Tilebox, for supporting this discussion. And then after that, we'll kind of dive right into the conversation. So why don't we start with, Jason, why don't we start with you?
Sure. Yeah. Hi, I'm Jason. I'm the CEO and one of the co-founders here at Colossus. My background is actually fairly technical, mostly in electrical and mechanical engineering. Among other things, I designed the software-defined radio that Capella Space uses for their synthetic aperture radar and some other functionality. And got started with Colossus about 4 years ago or so, really to bring modern computing to the space industry.
Stefan, why don't we go with you next?
I'm the Stefan, CEO of Tilebox. My background is in applied mathematics and high-performance computing. And I really started Tilebox because all the other components are really catching up or are leading the way, kind of. You can outsource payloads, satellite buses, and satellite operations, launch. But the software, the midstream part, transforming raw data to high-level data, is a real challenge.
Great. Gaurav?
Hey, everyone. This is Gaurav Bajaj. I'm the CTO and co-founder of Little Place Labs. We founded Little Place Labs about 3.5 years back when we realized that we can actually process space data in space, and we can deliver near real-time intelligence to customers and end users. So it's a lot about on the application side of things that we do at LPL. We understand customer problem statements, understand how raw imagery can be translated into insights, and something that could be used to take action in order to be more impactful. So that's what we do at LPL, and we are all about delivering low latency insights to end users. And our target is to do that in 7 minutes from the time of collection of imagery to the time where information and insights are delivered to end users.
Right. And then last but not least.
Hey, Aiden O'Leary, CTO and co-founder of Modulate Media, which we just publicly announced yesterday. We're a marketing and strategy for aerospace and deep tech firm. Past couple of years, I've been doing a lot of techno-economic mathematics, trying to figure out how a lot of these technologies actually reach their markets at the end of the day, is not just from a technology solution level, but from a actual market impact level. Because what I found at the end of the day was that a lot of it comes down to marketing, and thus is kind of the creation and drive for bringing a lot of that strategy into what we do here at Modulate Media, because the best tech in the world doesn't matter if nobody knows about it, cares about it, or trusts it.
Great. Definitely agree with that last statement there. Okay, so just a quick structure of today's discussion. We'll run about 40 minutes of conversation, and then we'll leave time for Q&A at the end. For the audience, at the very bottom of your screen, there's a Q&A button. You can click that Q&A button. I know some of you have sent in questions in advance, but if you guys want to use that Q&A box throughout the course of the discussion, happy to use it. If there's anything relevant that I can tie in during the course of the conversation, I will. So with that, let's dive in and start a little bit with some of the, well, let's start with a bit of problem framing. So there's a question to the group. So we all know that modern space missions are more data intensive than ever before. If from your guys' perspective, like what's breaking down in the traditional architecture today, and what's the cost of continuing to do business as usual?
Yeah, well, from the computing hardware side of things, the analogy that I like to use is thinking about it, if you're old enough to remember life in the 1990s, when if you wanted to meet your friend, you'd have to call their landline and arrange a time to meet, maybe at the mall. And if it didn't work out, you'd figure out something else another time. And these days, you of course just pull out your smartphone and come up with a new plan on the fly. That's really the difference in the level of compute that we're dealing with in terms of the status quo versus what we're able to deliver here at Colossus. A lot of the computing technology on orbit, even for flagship missions like the Mars Perseverance rover, they're using literally 1990s technology. Like the RAD 750, for example, is the same processor from the big colorful iMacs from 1998. So there's really a significant increase in computing power that's available at the hardware level. And then that brings with it all of the modern amenities of software development that the rest of my colleagues here can talk to.
By the way, Jason, before we turn it over to the rest of the group, I have a funny kind of random example. Everyone talks about how like, the iPhone today has more processing power than the Apollo missions. I saw something that actually hit closer to home as a kid. There was this photo I saw the other day of a gigantic computer, and it showed also side by side an Apple Watch, and it said, and basically it said that the Apple Watch today has more processing power than the computers used to render Toy Story, the movie, if you guys remember. So that was kind of interesting. But anyway, don't want to go into a tangent. I'll turn it. How about Stefan, from your perspective, what are you seeing?
The main challenge from our side that we see is the unseen complexity. So especially with distributed workflows or with heterogeneous compute environments, the requirements always start changing faster than you'd assume, and the data sources change over time, and this complexity can really lead to inefficiencies and can prevent engineers and from iterating quickly enough to meet the demands of the market or the business.
Gaurav, Aiden, anything to add?
No, I think the problem statements are well explained here, but it's about, once these problems are addressed, what capabilities appear and what does it mean for delivering some kind of value to users and customers. So, by being able to compute more data on the edge, you open a ton of use cases where, by transforming raw data into useful information on the edge and with ultra reduced latency, you can start serving problem statements that didn't exist before. Even a few years back, it didn't existed. So now customers and users can find value. And these customer users typically would be outside the space industry. One thing we always want to do and look into is how can we service real users on Earth? And that's where we can drive real value.
I'll add on to that is the hardware has advanced quite a bit to the point where it's like having a new iPhone, but we're running iOS 1 on it. All of this data that we're generating up in space, 100% of it needs to come down to the ground right now. Though there's some interesting stuff there we can get into later. But it's effectively like if you're looking for gold, mining all of the rock, all of the dirt, and shipping it all the way back to your end processing facility and customer, instead of extracting the gold and then just shipping that. Hundreds of times more data volumes are being passed than what we need. And this compute on orbit can help streamline that tremendously to then help accomplish 100x multipliers to the amount of customer packets that could be generated, and then revenue beyond that potentially.
So maybe let's touch on that a little bit more. Jason, this next one's directed to you. when you look at your hardware systems, what enables your systems to run, let's just say real-time AI workloads in orbit, and why hasn't this been possible before?
Yeah, so really, from our perspective, it's the hardware that was holding things back. You're going to be hard pressed to have enough excess compute capacity to run stuff that might have extra overhead, like orchestration systems, and certainly not have the capacity for running modern AI ML workloads. So really, it's the new hardware that's enabling this, and kind of big factor of that underlying everything here really is just the availability of launch, making it more accessible, cheaper to launch. That allows us to launch more hardware, launch more of these more complicated systems, have more power available for running these workloads, and really opens up a lot of options in terms of differentiation. In terms of what we're doing specifically, we look at hardware all the way down to the semiconductor level. And there's some really exciting things happening right now with the rise of new topologies like FinFET that mean that as the technology progresses, it actually gets even more inherently radiation resistant, as opposed to what we were seeing in the 90s and early aughts, where the newer technology was more susceptible to radiation. So that's one big factor. And then, yeah, just cheaper access to launch and specialization means that it doesn't make sense to shave every gram off your mission and spend years optimizing ahead of launch. You'd want to focus on time to market and get stuff out there sooner, get a good solution out sooner rather than wait for a perfect solution.
Stefan, I want to talk a little bit about data orchestration from your perspective. So Tilebox, and tell me if this analogy is not right, but you're kind of meant to be sort of almost like the brain between space and Earth, if I'm thinking about that correctly. Walk us through sort of the orchestration layer as you see it and why it's foundational for mission speed and efficiency.
So Tilebox is designed as a very low overhead foundational software framework. So less of a platform, more of a way to write software. It provides two core modules. One is datasets. That's a data access layer module. It ingests and structures satellite metadata. That could be telemetry, payload metadata, auxiliary sensor data, or on the ground, it could be data catalogs of intermediate or high-level data products. And with high-performance APIs and SDKs, provides fast, structured access to this data and extremely fast cataloging of data products on the ground. That's one aspect that it's usually just somebody wrangling a database and then struggling with the egress speeds and so on. The second module is workflows. So workflows is a parallel processing engine that enables the creation of dynamic tags or tasks as code. So you can dynamically create your parallel processing code, manages the execution of those tasks across all these diverse computing environments that could be on-premise, in the cloud, on orbit, across clusters. And this orchestration layer automatically handles the parallelism to utilize all this hardware that we have now, the Colossus Falcon with 12 cores and GPUs. How do you even code for that kind of hardware? And so also includes like task versioning for rolling updates and avoiding downtime and fault tolerance in the event of hardware failures. So it kind of decouples the data management and workflow orchestration from the infrastructure and from the specific algorithms that gives the developers then in the end the flexibility and control that they need to move fast.
Yep. Gaurav, let's talk about everyone's favorite topic, which is AI. Now you're building a layer on top of this infrastructure. How does real-time intelligence on board change what missions can do? You mentioned earlier you want to talk a little bit about what the unlock is here. What can missions do now, and how fast can they respond?
So this is great, actually. This is really an amazing time to be building applications like this, where you have so much of compute available. Because I remember when we started looking into this about a few years back, there were hardly any satellites which had any compute, and those were pretty basic. You'll probably talk about, taking an application, running it once and maybe multiple times over, but there was no concept of, DevOps, for example. In today's world, we know when AI models are generated, they work, but there are new versions of this coming out every few weeks, if not months. When we look at use cases working with our customers, we understand what kind of data is required. Working with that, we have scanned uh, the landscape to understand the different kind of sensors, the different kind of data modalities that are available, map it to the use cases, and for the right kind of imagery, we develop those computer vision models that help us uh, in object detection and event, change detection over time. Some of our customers really want that and want that information in minutes and not in hours and not in days. And that's where we are able to do that, all of this in a few minutes time. Uh, we had early, I mean, 2.5 years back when we did our initial demo, the compute was quite limited, and the uplink bandwidth is still a big challenge. While we all talk about downlink bandwidth, uplink bandwidth is also a big challenge, and that's why we focus on developing these AI models, which are really small and in size compared to the kind of machine learning models and computer vision models that are developed on the ground. So a lot of consideration to understand the constraints of the given space environment. Even though we have more compute available, uplink is really not appropriate or not enough. Nobody's asking for it, probably apart from us. Of course, there's more focus on getting data down, but there's always going to be huge data, and we need more compute. And I'm glad that we are at a place that where we can start servicing a lot more use cases with the help of more compute available. And now we are getting to the level, we are not just talking about running one application, but we are running multiple applications where we want to be able to update these applications on a weekly basis, just the way you would operate a cloud application. You can do that for satellites as well. And the infrastructure provided by Colossus and the orchestration provided by Tilebox, can really make it happen with us working collectively. I think it increases the market that we can actually target.
Is this how your kind of models remain flexible as missions evolve?
No, absolutely, because we never talk about, hey, we need to build these applications and upload it on the satellite, or let's say preload it before launch. We just want to make sure there is enough dependencies and infrastructure, both hardware and software on board, so that when a new customer comes in, we can develop those applications and uplink to the satellite. And it could be done in weeks' time rather than doing that over months. So while you have a really good flexible infrastructure that can support multiple use cases, we don't even need to know exactly which customers are we serving when we launch. But that's the beauty of having such capable and more generalized set, so that with the help of smart software, we can make the overall hardware and software combination cater to multiple needs, let's say.
Aiden, maybe you can give us your perspective on how this shift, what makes this what's possible from this shift from a user application standpoint?
Yeah, so I mean, there was a great example with the LA wildfires a little bit ago. I saw a post on LinkedIn where it was this research scientist talking about, like, I've dedicated my whole life to Earth observation, to AI, to wildfire science, and when it affected my home, I couldn't get the data fast enough for it to make a difference. And so exactly this, where it's like on demand, actually pulling from the right sources, getting it direct, shrinking that data packet down and streamlining all of the workflows so that it doesn't have to take potentially weeks in between of post-processing, human in the loop, et cetera, calling that data, selecting what comes down in the limited downlinks to try and figure that out and respond to these emergent conditions very quickly. There's a lot of capability there. There's a lot of questions over, like, hey, long term, how can, like, Earth observation actually, like, expand its market when it struggled so much with profitability? I think this exact near real time problem set is a huge part of it. And then on top of that, like, post analysis, and bringing it all together in a way that actually makes sense from an insights perspective, not just I have a data packet of this many gigabytes, let me send it to you package. So this whole stack of technology, bringing it together, actually serving the customer needs has been what's missing, because the upstream and downstream use cases, clients, capabilities have been a little bit disconnected.
Jason, you've flown your hardware before. What did that mission teach you, or what did you learn from that mission about performance in the wild, and how ready is this for broader adoption?
Yeah, so I'll answer in two parts. At a technical level, this was a great validation of our radiation tolerant system design. As far as we know, the system is behaving just fine. We don't have direct access to it, but we're in tight communication with the engineers, and everything's going great. And they've flown this unit on multiple satellites at this point. So it's a great validation at the end of a long road of engineering that went into that. But at a non-technical level, there's a lot of learnings from working with actual customers, deploying this in reality. And you can put together all the documentation and prep work that you want, but when you actually get a real customer asking real questions, it really helps sharpen that documentation, and it's a great way to know what's actually really important. And we've been doing a great job with that. Like I said, multiple orders coming in since then, and it's made all of our processes better. Some of the things that Gaurav was talking about ring true in terms of uplink bandwidth constraints. Normally that would be a downlink bandwidth constraint in terms of getting the raw data down. But if you want to load new libraries, new software images, that's really been one of the limiting factors operationally.
Yeah. Stefan, from a systems perspective, what gives you confidence that this is a repeatable solution and not just kind of a one-off integration?
We designed it to be repeatable because it operates as a framework within the existing infrastructure. So it's open, accessible with a free community tier. We designed it from the get-go to be agnostic to compute environments and sensors and give the users flexibility to work across these different environments. Key factor kind of to make it repeatable is the speed and flexibility of creating custom data sets. So this integration effort is really low. It's a matter of minutes, and workflows as well. So users can quickly create their own dedicated data types, which then can be accessed through all their standard clients in both Python and Go. And for workflows, the same. We support multiple languages. We enable the ability to choose the best language for each task. And that might be different for every mission, but this kind of architecture combined with the low overhead makes for a great foundation on even the lower end of general purpose compute modules.
So question to the group, do you see this evolving into some type of standard developer stack, something others can easily build on in the future?
Yeah, that's certainly our intention here at Colossus. We're starting with the hardware, but the hardware doesn't do anything without the software. So we're always keeping an eye to how we can support the folks building the software infrastructure and the application software. And for us personally, we use standard library components as much as possible, even for things like our telemetry and our power state management. We prefer to use the open source Linux tools for all of that, specifically to make it easier for developers. So it just looks like a regular computer as far as they're concerned. And that not only speeds up development, but it also opens up the pool of developers. So you don't need to know something specific about some weird space computing architecture. We can just take advantage of all the work that's being done in computing in general.
So let's kind of shift gears for a second and talk about a bit more about real world impact. Jason, Stefan, maybe we can start with you guys, or anyone else can feel free to chime in. But have there been any missions where multiple layers of this stack have worked together?
We've had edge computing devices active on the ground for months. There's an upcoming opportunity where we'll fly together either at the end of this year or early next year.
Yeah, I can.
Unfortunately,
Go ahead,
can't get into specifics on that, but this might be a good opportunity to mention the upcoming demo that we have next week at SmallSat. So if you're around Monday morning, come by and you'll see a few of us, all of our code working together in a real world example on dev kits.
Aiden, were you gonna say something?
No, just excited.
Okay.
I was just I was just about to add that I mean, like Jason was alluding to earlier, the devices, they have flown on multiple missions. We've also been working with our partners to demonstrate the capabilities of deploying applications, reiterating on top of them, and showcasing it. So, with a stack that's, let's put it this way: before launch, the stack didn't exist, but it just had enough uh, enough uh, uh, supporting infrastructure, both hardware and software. Now you build applications on top of that. So we have recently, over the last year, we've recently demonstrated how we can, turn a raw imagery. This is for EO Earth observation use cases. Turn imagery into insights and deliver that to the ground in about 19 to 23 minutes at average. Our target is 7 minutes, which we are quite positive we'll be achieving. But all of this is possible because of the multiple uh, 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 layers of hardware and software, stacked up and working together. And we're still working on new plans and new ideas so that it's not just the end for one kind of demonstration, but this is being done for customers and for users who see the capabilities. And now we are looking to take those initiatives forward into much longer projects. So for us, I think it is going to keep all of us busy. I look forward to the new cool shiny gadgets that, Jason and the team is going to come up with at the SmallSat. So quite excited, which is going to give me more compute so I can do more of that. And that's why I need Stefan's and the orchestration layers, because we want to make sure we squeeze every bit of compute from the hardware. And that's very important because energy and power is limited, and there's always going to be more data than compute. And then for us to have really good capable hardware, smart orchestration layers, so we can deliver something that our competitors can't. And that's why I think three of us, while we look like all in edge computing, we are not competing. We are actually complementing each other to build something much more capable.
Jason, let's talk about the shiny gadget for a second. How does putting powerful compute in orbit change the economic model for space missions? And I know, Aiden, you also spent a little bit of time, I think, if I remember correctly from our earlier conversations, you've spent some time on the economic side of the cost calc. So wherever you feel like you can chime in, please do. But Jason, let's start with you.
Yeah, so basically there's two ways that this really helps economically. There's making existing operations more efficient, and then there's opening up new operations and new lines of revenue. So in terms of making operations more efficient, that's what Aiden was talking about. Don't ship the ore over and process it later. Just refine the data on board. Turn that hundreds of gigabytes of hyperspectral data into a quick kilobyte text file explaining that the pipeline that you're monitoring is fine. So that's 1,000,000 to 1 reduction in data right there. And then in terms of new operations, this is things like autonomous operations or satellite servicing, applications where you can't afford the latency that comes with relying on ground computing for your mission. So one of the ways that I put this, during the Apollo program, we had rendezvous and docking. We had an onboard processor there. It was called the command module pilot, and he would just look out the window and jockey the stick to get the spacecraft to dock. Well, nowadays, if you want to do that robotically, without a human crew, you need the computing on board to be able to do that. So there's all sorts of new revenue streams, new operations that are enabled by having this availability of computing.
And to quantify, sorry, go ahead.
Go ahead, Aiden. Go ahead.
Quantifying that, like specifically in terms of how do we take it from what you're doing today? Can that be a lot more cost efficient? So Earth observation already struggles with profitability. Payload actually had some great research on this with the profit and loss type stuff of the different public companies. And generally speaking, like one of the most expensive assets of running an Earth observation company is downlink. It is quite expensive to talk to all of these different ground stations to try to get everything down in that one packet, and it limits the number of operations you can do to like a pass per orbit or on that level, instead of being able to take data from everywhere that you're passing over. And so that 1,000,000 to 1 conversion is phenomenal. And even doing something less like 2x to 16x to 2x to 16x, what I found was 16 to 30% reduction in overall lifetime costs of a constellation. That's incorporating the cost of the satellite launch, overhead, et cetera, using some parameterized stochastic modeling. From the near real-time operations aspect, where you just need to send down a little text file, say 200 times reduction, there we're talking more than 30% to, in some edge cases, 60% cost reduction of the overall satellite if you have really small satellites. So it enables a lot more business models and use cases to serve these different emerging things where you don't need to buy a whole data packet of multi-kilometer by multi-kilometer swaths. You could be like, hey, is my thing leaking? And it can say no. So like that whole process where it's like, where are the customers? I think it's too obtuse for them at the moment to actually be worthwhile. There's too much involved, and this whole stack of streamlining all of the middle bits, operations and end customer experience, like it can make what you're doing today enough that in some of these cases, on average, you approach profitability. And then in the edge cases, you break profitability with what you're doing today without even incorporating any new revenue. Once you incorporate new revenue, which is potentially hundreds of X, if you then can do your entire orbit, the question is who is paying for all that, but that's the upper bound of the capability we're talking about with the hardware that exists on orbit today.
Yep. Okay. Well, so question for the group. From your perspective, what part of the value chain benefits the most from this architecture? Is it cost, speed, or risk? And I know you can make an argument for all three, but let's just say near term, where is the most value being derived, and then maybe what does that look like long term?
Yeah, I'm going to be a little bit cheeky and pick two here, which is cost and speed. But because time is money. But really, what we're seeing is by moving to one of the benefits of having more compute and having the orchestration and the software infrastructure available is really reducing that time to market. So it used to be if you wanted a new satellite, you'd have to spend 2 to 3 years at a minimum designing the satellite and getting it ready for launch, and then wait a while for launch. These days, with transporter missions going up every quarter, for example, you can get to space much faster. And with the availability of more commodity hardware that is plug and play and just works together, the folks building satellites can focus on what they do best, which is doing the cool stuff in space, and not have to spend years designing custom compute hardware, for example. And that reduces costs, obviously, gets you revenue faster. So it's all kind of related.
Who anything else to add from the group?
No, I would definitely
let's
support what Jason said. Latency is the big thing for us. We focus on making sure our customers get what they want, much more quickly than they are currently used to. And of course, all of this will additionally translate into cost savings as well. So for us, every use case where we can address latency are the more practical use cases in the near term. And once we have the whole stack matured and deployed on multiple assets across, the unit economics will make sure that the cost comes down. So it becomes more practical for other use cases as well to start leveraging it. Because my view is that we should be talking about insights and processed information from space at the same cost as imagery, the way it's delivered today. So there is no reason why that cannot be done. So it's not out there yet, but we are fully confident that it'll be the case soon.
Yeah. Let's talk about the customers for a second. Where are you seeing initial interest, government or commercial?
Yeah, for our part, it's a bit of a mix, kind of like most of the industry. It's maybe somewhere around like 70-30 government commercial. We definitely have customers who are doing their own totally commercial constellation. They have their own commercial customers. Maybe they also sell to the government. And then on the government side, we're seeing a lot of interest due to our position as the premier hardware vendor in the US. So any sort of DoD type missions that are concerned about supply chain and keeping things in the US, we're a great choice for them to support all sorts of missions, including stuff that you might see from like the Space Development Agency, for example.
Got it.
From our side,
with
from our side, it's for sure the earlier adopters are commercial. It's mostly companies that are focused on moving fast and reducing risk, like the risk of being able to deliver what they promised, the risk of losing focus from the business and focus from the algorithms and the core of what they're doing, to things like orchestration and developing their own in-house frameworks and whatnot. So for sure, on our side, it's commercial at this point.
There's a question from the audience that I want to take just because it's relevant to our next topic. What challenges are you three facing with regards to manufacturing the technology, meeting timelines and schedules, and keeping costs down? How are you overcoming them?
Yeah, so a couple of years ago, we had the great chip shortage, if you're familiar with that, where supply chains were very strained. That's mostly been reduced now, but still a concern for us. In general, we want to move very quickly, and we need suppliers that can keep up with that. So I'd say lead times for some key components can be a challenge for us. And then beyond that, it's just working with our customers to make sure that they get what they need, building excellent documentation and so forth. But yeah, there's many challenges. I could go on for hours, but open it up to the group.
Or as a software company, we don't have these kind of lead times when it comes to deliveries and input products, but still, like, the issues on our side. So we do move fast, and we do that mostly by keeping our focus and not competing with our customers, and partnering up and creating an ecosystem of players that are happy to work together. I know this is oftentimes not so much the common way to do things, and vertical integration is kind of a meme in this industry, but by keeping the focus, I think we can all move a lot faster.
Jason, I want to do a quick follow-up with you. What's a engineering lesson that you've learned building high-performance space-grade compute?
Yeah, I think the big one here, it's not a technical lesson, but it's much more on the non-technical side, and really, documentation is underrated, and focusing on that and really nailing the customer support experience, making sure that our customers feel like we can act as an extension of their engineering team to support them, let them do all the cool stuff in space. We'll handle the compute hardware. That's been probably one of the biggest learning curves for us, is figuring out how our customers digest the material, making sure that we're explaining what our hardware can do, how to take advantage of our hardware to the greatest extent. So it's a lot of this non-technical stuff. I think for our team here, we come from a background of designing lots of high-tech solutions, and so the technology is almost kind of the easiest part, and it's all the soft skills and everything else that goes into making a good business.
I would double down on that for sure. Like the problems I've had as a systems engineer over the years have always been like, there's no price transparency in this industry. It is very hard to be able to assess which components or things you should go with on what timeline, because you basically have to commit to buying X number before they give you like an actual quote for it. And we can talk about why, but effectively the economies of scale have not been there in the industry to date, and we're starting to see the emergence of that, which is really exciting.
What's a common mistake that you guys see from startup founders, given what is what the capabilities we have today versus the way certain companies are building their architectures?
I think the build versus buy, sometimes the input cost of build, which is like human resource, like the cost of building and maintaining, and like these personnel costs, they're just like free for people in their mind. They're not considered many times.
Yeah,
that's at least
okay.
from my side an observation. Yeah.
Anything else from the group?
No, I would agree with that. Basically the calculation you're making at that point is, do you want to spend millions of dollars and hire up a team and take a couple of years to design a perfect solution for yourself, or get something off the shelf in a matter of a couple of months?
Okay, and then one last question to the group, and then I'm going to turn it over to Q&A. If this stack becomes standard, what's the new class of mission or product you think this will enable, 5 years from now?
Yeah, I think we'll see a lot more exciting stuff happening with Earth observation in particular. I think that's going to be that can benefit the most from having a lot more onboard compute. If we're talking a 5-year horizon, we're looking at satellites that can operate autonomously, that can provide data insights to the ground instead of raw data. And then, for myself, looking ahead even further, I'm a big space nerd, obviously, but looking ahead towards planetary exploration and just seeing what Perseverance showed in terms of using a cell phone grade processor for navigation, and just imagining the future that is coming for space exploration of the solar system. It's a little bit maybe beyond 5 years from now, but something that I find exciting.
I think this stack will unlock all kinds of new business models. It'll provide bigger margins. It'll enable in-orbit space debris monitoring, which requires a lot of compute. It'll lower potentially minimum order sizes, which is in Earth observation is such a pain that you always have to order hundreds of square kilometers, even though you're interested in your construction site or something. And it'll enable better monitoring coverage. So any kind of monitoring use case requires kind of the payload to be on for a longer periods of time, and then you can't downlink all that. So you kind of need to transform it into you need those this data reduction step.
On the near real-time front, I'm really excited for like space-to-space satellite link, because we talk about like, the uplink problem. You have to be able to get like the software packets there. You have to be able to get user requests there. If you could just hook into something like a Starlink or a Kuiper, and get those like responses near real time, how much more efficient could you make that whole workflow to then actually start and then send back that text file for that same thing to get it in minutes, and not have to rely so much on like having all of these different ground stations at the right whatever. You can optimize a bit more for actually the space-to-space data link, and see the beginnings of Jason used this term on one of the pre-calls, outer net. because space, like we talk about latency, fiber optic cable on the ground, it goes at 2/3 of the speed of light. So right now, like we could reach Stefan in Europe faster through space than we could through the ground because light travels faster through that medium. So we could start seeing the emergence of world connectivity faster through these space data layers using higher and higher data rate transmissions as well beyond like laser comm struggle in atmosphere. So we could use those emerging beyond that to UV, X-ray. This is getting more like 10, 20-year time frame, but like you could have whole internets and data centers up there communicating near real time with low latency compared to what's possible in atmosphere and through fiber today.
And you mentioned a keyword here, data centers. I think the long term, there's like long term, this is like an inevitability almost for if we continue to develop our technology and the needs for compute and so on. But you can have the version of that works already, that you can have already, is networked multi-node compute or satellites that contain multiple compute nodes that are networked, and so you can have a compute cluster on a small sat. You can do that already right now with this stack. That's the current version of this idea.
So I have some good news and bad news. The good news is I have a ton of questions I need to get through. We just got in. So between the questions I have existing and then the ones that just came through, the bad news is we only have 10 minutes to get through as many of them as we can. So I'm going to go through them, try to keep your answers tight, and then let's see what we can do. Okay, one question which Stefan, you were starting to allude to. What is the ideal computing storage and computing capability you envision for an orbital data center now in 5 years and 10 years beyond?
Computing, storage, and computing capability. It has to be resilient, so you can't really have to have very reliable, systems in orbit. If nodes go down, you need to load balance. If storage modules are failing, you need to be able to recover or have like error correcting codes and so on. I mean, a lot of that is already the case on clouds on the ground, but you need it like times 10 in space for sure. And then so it's from my side. Yeah,
Yeah,
I don't want to hold too much time. Yeah,
very expensive to send a tech up there to swap out a card. So reliability is key. And I would envision the use cases for this being processing data generated in space, and then just kind of an extension of the specialization that we're seeing.
What are your thoughts on orbital data centers conducting inferencing missions for terrestrial users? Also, what about having orbital data centers to conduct the edge computing instead of having on every single satellite?
Yeah, so I think ultimately as the satellite to satellite networking becomes more connected, more viable, that we will see specialization. I think right now, because that network's not there, each satellite basically has to carry its own compute with it. Moving forward, I could definitely see there being satellites that specialize in processing space data so that we don't need every satellite holding on to all of the compute. I still think you're going to want to have a mix of compute right there at the edge at the platform that's generating the data, maybe to do some quick filtering and prioritization, and then have more specialty systems that could aggregate data from multiple of those satellites and provide insights that you can only get with multiple satellites.
Okay.
I'll also,
Go ahead, Gaurav.
I'll also just add one more point there. One of the things we've been looking at is a lot of edge compute is mostly on the data generated in space. For now, I think it's going to be a function of cost, whether it is cheaper to move data or it's cheaper to compute it on the same asset where the data was generated. I think it is going to change over a period of time. Initially, we're looking at that it's only or mostly going to be data generated in orbit, which is computed locally. Then it might move to data generated in orbit and move to another orbital asset. And hopefully in about a 5 years time or more, it'll be terrestrial data that'll be then moved to the orbit for processing. So it's going to be a change we will see, but I think the use cases and the business models will keep evolving with this, and I think I'm quite keen to see how everyone plays, their own crucial roles as this matures.
I think data centers for edge computing are interesting, especially if you need some sort of ground truth or reference data sets that, like as Jason also mentioned, you want to do data fusion with those, then it's super necessary because you don't want to store that redundantly on every satellite. But until those networks are, and the hardware also for networking and the networks themselves are more readily available, I think directly on the satellite is the way to go.
So this next question is about Starship. We know that it's having some challenges, some challenges today, but when Starship is eventually operational, and let's assume it will be operational, question for Jason, what is the impact going to be on the compute hardware side?
Yeah, it'll certainly make it easier to get more compute to orbit. A little bit of a nuance there. We're seeing this already today with the impact of the Falcon 9, but basically satellites are trending larger, like physically larger. So it used to be a lot of 3U CubeSats, kind of loaf of bread sized, or small sats that were kind of the size of a mini fridge, 50 kilograms or so. We're seeing a lot more satellites move up, jumping up to 200 kilograms or even up to 1-ton class satellites. When Starship comes online, I would expect to see a similar growth in the size of these satellites. And that just means a lot more resources. So more electrical power, more thermal rejection capability, bigger sensors generating more data that needs more processing. So everything will continue to get larger and larger in scale and capability. But at the end of the day, you'll still need reliable compute because, like I said, sending somebody up there to swap units out or setting up new hardware is still going to be very expensive.
So this is a question for the group. How hard is it to integrate this stack into an existing satellite or mission plan? Do you have to design around it from day one?
Actually, no, I don't. So at least from our side, you can adopt individual components based on your need. You can use the data access module for high performance data access, or you can start with or just the workflows to orchestrate complex data processing tasks. Regarding Colossus and Tilebox, we have a pre-integration, so there's nothing to do there. This is already works. And Little Place Labs, and actually with the demo that we have next Monday, we'll showcase the same. So this is ready to go. Yeah, quite fast.
All right, Stefan answered for everyone.
Just about the edges to those. So if I don't speak for the other companies.
Anything else to add from anyone on that one?
Yeah, just one note that adding onboard compute, the best way to take advantage of it is to design that in at the mission concept layer. So bolting it on at last minute, adding some extra computing is not nearly as useful as designing your entire mission from the ground up to take advantage of onboard computing. So we're starting to see that now.
Yeah, I would just add to the fact that while the earlier you plan, the better, because the ConOps looks quite different for the way you would use it for a satellite, for an asset where you're just collecting imagery, compared to when you start deploying software and running software on a need basis. I would even go to the extent saying that once you have an asset on board, it can take you 6 months to a year to get the ConOps working efficiently, because there's so many layers of software that needs to be worked upon. If you don't do it early, it might just take longer and could be more tricky because the asset is already in the skies. So earlier is definitely better.
You'll see the best margins from earlier. Like it gets into how you design for how much electricity you need if you're using larger compute. Same with the data link, how you design all the different channels and everything, and which ground stations you communicate to, how often you want to communicate, and what data volumes. Like thermal engineering, I think we're going to see a lot if people keep talking about data centers into the future. Like that's a very problematic one in space. Like there's a lot that benefits from hyper optimizing the thing. It was interesting in reviewing all of the different companies in EO. There was the only ones who were actually profitable were the ones who hyper optimized their satellites for very specific use cases from the beginning. And so I imagine we're going to see that where the biggest, best performing players are the ones who adopt early.
Got it. Okay, just as we close here, one final question for every person here, which is, what's a space innovation you're most excited about personally?
Yeah, personally, I'm really excited about the design work that's being done in nuclear fission for providing power for missions beyond Earth orbit and supporting robotic and human exploration of the solar system.
I would, the one thing I'm excited about is space tourism. I'm trying to make sure that I am able to save enough money and the ticket price comes down so that in my lifetime, if I can pay a visit, and my definition of going to space is one orbit. So hopefully I'm not old enough yet.
I'd say in space manufacturing, like ICM in general, I think we're constrained a lot by what fits in the nose cone of something at the moment. It would be really cool to be able to distribute that effectively over several different missions and build crazy, crazy capabilities. And then eventually extend that to things like ISRU, getting stuff cheaper from the moon than you can from Earth. Done a lot of work there, and just perpetually excited about what we could do with space if the economics work.
Then Stefan, anything on your end?
I like that space becomes more accessible and that, that becomes more, that we learn more about Earth and about the environment. We start becoming more structured in our access to space when it comes to debris and when it comes to all these constellations that are intermingling right now. I like that a lot. I like this can enable space tourism and can potentially, make it possible for us to go to space.
Amazing. Well, gentlemen, thank you so much for joining us today. Thank you to all the attendees for listening in. We will have a recording of this webinar sent out shortly after this. So thank you guys for joining. Thank you for participating. And thank you to Colossus and Tilebox for helping support this conversation. So thank you guys, and until next time.